the CERIAS Security Seminar Series for January 28th. It's my pleasure to introduce Ryan Riley, who will be talking about a memory architecture to prevent code injection. This is a good chance for you to see exactly what you become with a Purdue education in information security. Ryan has been here for his bachelor's degree, got his master's a couple years ago, and will be completing his PhD this year. So, welcome to Brian.
Thanks. So yeah, like Dr. Clifton said, I've been here for, it's my 9th year at Purdue. I'm quite anxious to graduate and leave. But I am a PhD candidate in computer science, and August looks like the time frame for when I'll graduate. And what I get to talk to you about today is actually kind of the core of my dissertation work. So I'm excited to be able to do that. Now the title of today's talk is an alternate memory architecture for code injection prevention. So it's kind of a big title with lots of terms in it, and we'll hopefully define those as we go on through. But just from the title itself, you can kind of look at it and realize that I'm talking about the code injection problem, and I want to be able to prevent it, and the angle that I'm looking at is from the memory architecture approach, so the architecture of the computer that these programs are running on. So before we get going too deeply, I want to discuss what is code injection. For those of you who aren't familiar with it, or for those of you that are, you can get an idea of the definition I'm using for the rest of this talk. So I want to kind of describe it by illustrating it with an example. Imagine we have a running process, and it has instructions and it has data. Now, as the process runs, the instruction pointer just slowly moves through the instructions at a normal pace, executing the instructions as you would expect a program to. Now, let's imagine that we have an attacker somewhere, and that our program actually has a flaw, some sort of error in it, that will allow him to both add arbitrary information to the program's data, and at the same time move that instruction pointer to wherever he wants. So the first step for him is to add his malicious code onto the end of the data section. And now that he has his code there, his next step is to simply move the instruction pointer to point to it. So if he can actually pull this off, then I call this a code injection attack. So it's where he adds malicious code into a running process and then gets it to execute. So at this point, the attacker has managed to have arbitrary code executed at the privilege level of the process that had the flaw. So how is code injection used? If we know that code injection is the problem I'm tackling, what does it look like in the real world? So usually you combine it with some sort of memory error. And the memory error is what allows the attacker to either add his code and hijack the instruction pointer, or just hijack the instruction pointer. So there's a number of these that are out there and available. For examples are things like a stack overflow, format string vulnerability, a heap overflow, or a double free. So these are terms you may have heard in the news or on vulnerability reports. But if you take one of these and you combine it with code injection as your technique, then what you get is some sort of valid attack. An attacker may have the goal of spawning a shell at the privilege level of the process that he compromises, or it may be some sort of self-propagating worm attack. Those tend to exploit code injection. Or it may be, in the case of compromising an operating system kernel, rootkit installation. So why is this a problem? And what I mean by this question is, what about computers makes them vulnerable to code injection? So many computers are actually inherently vulnerable to code injection because of the memory architecture that they use underneath. That architecture is called a von Neumann architecture. And in a von Neumann architecture, there's no distinction between code and data from the processor's perspective. So the processor can write to a given memory address as if it's data, and it can fetch from it later as if it's instructions, and the architecture makes no distinguishment. So that means that your malicious code could come from data sources. They could come from files, they could come from the network, it could come from a user interacting with the system. So any of those could be used to add malicious code to a system. So a von Neumann architecture simplified kind of looks like this. So we have a physical memory space, just one physical memory space, and it has both instructions and data scattered throughout it, and the processor issues all of his instruction fetches or his data reads and writes. Any memory access just goes to that physical memory space. So there's no distinguishment, like I said, between code and data. Now, one big flaw in this architecture is, like I was talking about, that it's vulnerable to code injection because of the fact that the processor sees everything the same. But there are other advantages to it. One of the major ones being that it has a huge install base. So most commodity computers that you're going to use, like your desktop, your laptop, the server that your favorite website runs on, all of those are going to use a machine that has a von Neumann memory architecture. But not all architectures are von Neumann, and they're not all inherently vulnerable to code injection. So another architecture that's not vulnerable is called a Harvard memory architecture. So in a Harvard memory architecture, we have two separate memory spaces, physically distinct, One's the instruction memory and one's the data memory. You're actually probably already familiar with this, you just don't know it. Most embedded devices, or at least a lot of them, will have this Harvard architecture. So you'll write your code to a little EEPROM chip, and you have a little bit of RAM there for processing data, but the two aren't mixed. So when the processor issues an instruction fetch, it goes to some sort of code memory, and when the processor issues a data read or write, it goes to a data memory instead. So the processor actually can't address the data memory for an instruction fetch, and it can't read or write from the instruction memory. It's simply not a feature available on this architecture. So given that, the Harvard architecture is actually immune to code injection because it doesn't have the necessary features required to support it. So what if we could have an architecture that has the wide install base of von Neumann and the immunity of Harvard? And that's kind of the core of my dissertation work, is saying what if we could put together an architecture that could have the best of both worlds? So what I'm proposing is a new architecture that has the immunity of Harvard, but is constructed on top of a von Neumann architecture. And it looks something like this. We still have one physical memory space, but we put restrictions in place to ensure that the processor can only access a certain portion of physical memory when it's doing instruction fetches, and has to access a different portion of physical memory for data reads and writes. So the instruction fetches can't go to the data section, and the reads and writes can't go to the instruction section. That's kind of the ultimate goal of our architecture. So on this new architecture, what would a code injection attack look like? So we have a normal process layout that looks something like this, with our instructions and our stack and our heap. And now imagine that if we instead split it up, and this would all be in one physical memory, but we're going to keep it split for the illustration purposes, so that all the instructions are in one portion of memory and all the data is in another. So if an attacker manages to compromise the running program because it has a flaw and take his attack code, when he goes to inject it, the processor will address the data portion of memory and it'll write his attack code there, because that's where all data reads and writes go. When he later hijacks that instruction pointer and gets it to point to the added malicious code, well, the processor will address the instruction space of memory, and it'll do its instruction fetch and find that his code isn't there. And if his code's not there, then his attack fails. So if we can have a system that operates like this, code injection simply won't be a possibility. So I've made some important claims about this particular architecture. One is that it can be constructed on top of the von Neumann architecture. And that's what I need to prove in the rest of this talk. And I'm going to do that by describing how it can be built at both the user level and the kernel level to prevent code injection attacks. So first is at the user level. So my goal here is to take an unmodified program that may have existing flaws that would allow this attack to take place and run it in such a way that it'll be on top of this architecture. I don't want to require any hardware changes, so I want to be able to do this on a completely existing machine, and I want to enforce it in such a way that the currently running application can't circumvent this architecture, which means that I have to enforce these rules at a level more privileged than the application itself. So in the case here, the best place to do that is in the operating system. The operating system is more privileged than the application, so he'll be able to enforce these rules. So what's our problem space? If we're dealing with code injection at the user level, what do these sorts of attacks look like? Well, they actually look like what I've already described to you, where the attacker basically hijacks program flow, runs his own malicious code of some sort, and he uses that to either gain new privileges to a system he didn't already have privileges on, or to elevate his privileges in some way on a system he already does. So as an example, consider a running system that has like a mail daemon on it, and that mail daemon has a bug in it, and the attacker remotely connects to it, exploits that bug to add his own code and get it to execute and spawn off like a root shell. Now, our goal is to be able to run that vulnerable send mail system as is without any changes and be able to prevent that attack from happening. So there's a lot of previous work actually on dealing with code injection at the user level. One approach is language level approaches, so dealing with things like Java or C#, and their goal is to remove all of those memory errors that attackers tend to use. And they actually do it quite effectively. The only main downside actually to language level approaches is that they're not widely adopted enough. So there's still a significant amount of existing and even new software being written in languages that aren't safe in this way, languages like C, and so these approaches don't work to help prevent those attacks. Another type of approach is a compiler-based approach, things like StatGuard or ProPolice, and basically with these sorts of approaches, the goal is to take one particular memory error and architect the compiler in such a way that it will remove that flaw, or at least